All right, let's get started with section 8.6, which is normal distributions. All right, let's first talk about what normal data is. Before this year, we used to do an activity the day before this lesson where students would use a random number generator to create random numbers between 1 and 10. They would generate 10 numbers. They'd take the average of those 10 numbers and then write it down on a sticky note. And they do that 10 times. So each student had 10 sticky notes with averages of 10 numbers from 1 to 10. Then we put that sticky note on a giant number line on the whiteboard, and you can see that's the image here, okay? And when you do that, what you find is you have a lot of the averages are around 5, which makes sense, right? Because you're taking numbers from 0 to 10 and you're averaging them. Some of them are slightly to the left of 5 or less than 5. Some of them are slightly more, and there's even fewer still that are closer to 10. Very few are, if any, are less than 2 or 3, and very few, if any, are greater than 7 or 8 going to the right. Okay, so that type of data is called normally distributed data. Okay, and it creates what's usually called a bell curve. All right, we've looked at some of these in the context of histograms before. All right, so we know that the mean and median are equal to each other for symmetric data. Standard deviation we're going to talk a lot about today, finally, and that is a measure of how spread out the data is. We've also talked about histograms and probability distributions briefly. So today we want to answer questions like this. If men's height is normally distributed with mean of 69 inches and standard deviation of 3 inches, out of a sample of 100 men, how many are likely to be above 6'3", or 6'3" tall? Okay, and that should not say foot tall. All right, so that's the kind of question we want to answer. Let's dig into normal data and what's going on with the bell curve here. So this is the bell curve, or this is a normal distribution technically. Okay, and the way to understand this chart or diagram here is that 0 is 0 standard deviations away from the mean. Okay, so whatever value is here, that's your mean. Okay, and then whatever value is over here, 1 tick mark to the right, that is 1 standard deviation to the right. So if the average in our example here was 69 inches, then 1 standard deviation to the right would be 72 inches. All right, and what that means is that from 69 inches to 72 inches, 34% of men will be between those heights. Okay, from a random sample, right? And that just keeps going. So if you want to know like how many men are between would it be 66 inches and 72 inches, there are 68% of men will be between those heights. Okay, so basically, in general then, 1 standard deviation away from the mean in either direction, 68% of people will fall in that range of men in our example. But all right, 95% of people will fall within 2 standard deviations of the mean. All right, so that's almost everybody will fall within 2 standard deviations of the mean. Within 3 standard deviations of the mean, you get even closer to everybody. 99.74% of people will fall within 3 standard deviations. And then finally, outside of that, to the right of 3, almost nobody. So this is 0.13%. So that's barely 1/10% in either direction. Outside of 3 standard deviations, very few people. Okay, those are what you might call outliers. All right, so this number down here at the bottom, when it's just written like this, where the mean is at 0 and the standard deviation is 1, the number of standard deviations away from the mean is called the z-score. Why z-score? I'm not really sure. Number of standard deviations away from the mean is what it means, and that's a lot to say at one time. So z-score is simpler. Maybe that's why. All right. So let's go back to our question here. Height is normally distributed with an average or a mean of 69 inches, standard deviation of 3. Let's fill out the normal curve here based on what we just learned here and the information we've got in the problem. So 69 inches is the average height, the normal or of the average American male. And so 3 inches to the right, that'd be 1 standard deviation. So this would be 72 inches. This would be 75 inches, and this would be 78 inches. Okay. Going back the other way, we'd have 66 inches, 63 inches, and 60 inches. Okay. And so the question that we're trying to figure out is, out of a sample of 100 men, how many are likely to be above 6'3" tall? Well, what we need to know is what percentage of men are above that height, and then we'll apply that to 100. Okay. So we need to find 6'3" in inches. 6'3" turns out to be 75 inches. Okay. So 75 inches is right here. That's 2 standard deviations away from the mean. So that'd be a z-score of 2. And just to reiterate this, so here would be a z-score of 0, 1, 2, 3, -1, -2, and -3. Those are z-scores. All right. And so we want to know from 2 standard deviations away from the mean to the right, right? We want to know what percentage of data lies to the right of 75. Okay, well, we can go over here to our little chart. So here is 2, the line for 2, and we've got 2.15% of data from 2 to 3, and then 0.13% of data the rest of the way. So that totals to be 2.28% of men, okay, or taller than 75 inches. And so that means that we can infer that out of 100, 2 or 3 men are taller than 6'3" inches. Right? Okay, so that's the basic mechanics of the normal curve. We're going to pause that for a while. We'll come back to it in a second. Let's talk about z-score for a little bit. Z-score is computed by taking whatever the data point is, subtracting the mean, and dividing it by the standard deviation. Okay, that's how we get this number that's between like -3 and +3. All right. Symbolically, x is the data point, mean is mu, and this lowercase sigma is the standard deviation. So some of the problems will just ask you to play around with this formula and solve the missing parts. So in this one we have z is 1.2, we have x is 42, sigma, or standard deviation is 5.1, we want to find mu. So we just drop everything into the formula and solve. So we have 1.2 is equal to the data point, which is 42, minus mu, which I don't know, divided by 5.1. 5.1. And then we just solve this for mu. Okay, so times both sides by 5.1. And on the left I get 6.12 is equal to 42 minus mu. Subtract 42 from both sides and you get -35.88 is equal to negative mu. And then times both sides by -1 and you get this. Mu, the average or the mean, is equal to 35.88. Right? And that's it. So again, there will be several problems like that where you have to just kind of plug in parts of the formula and solve for the missing part. All right. Now, we did a problem up here where we were trying to figure out how many men were greater than a certain height. Okay. But we could ask questions like how many men were less than a certain height, like maybe less than 67 inches, for example, or 66 inches, something like that. We could ask questions like how many men, or what's the percentage of men are between values, like maybe between 63 and 69, right? We could ask questions like that. And so to do that, that covers all 3 situations. And to do that, it's laid out here how to do that. Now this command right here, this is for a TI 83, 84, etc. Okay? In Desmos, it's a little bit different. In fact, it's a little bit easier. In Desmos, use the command normal, DIST, and then you put in the mean and the standard deviation, just like that. And then you want to check, there'll be a checkbox, I'll show you in a second, find CDF. All right? I'll show you what all of that looks like here in a second. So let's apply this to a problem here. So if height is normally distributed with mean of 69 inches and standard deviation of 3, what percentage of men are likely to be above 5'5" tall? So real quick, that's 65 inches tall. So what percentage of men are going to be above 65 inches? Well, let's do this in Desmos. All right, so here is what happens when you type in normal distribution. All right, you get just a standard bell curve. Now I've zoomed this in so that we can see that we've got the z-score along the bottom. In fact, I wish I could turn on. Let's go step 1. All right, so you can see the z-score goes along the bottom, or out to -3 and to +3. It actually goes beyond that, but there's just not much data over there. Okay, so I'll share this with you where the scale is set right and everything. But right now, that's just your standard normal table, or normal curve. What we want is it to be set up for our situation, which is 69 inches for the mean and 3 inches for the standard deviation. So I plug that in. I make sure that the box is checked, although that won't affect the graph at all. Now, this is at 0. My average is at 69 inches, so I need to go all the way out to 69 inches to find. Let's actually turn this off for a second. And of course, you can use the little wrench as well. Okay, so there's our curve. All right, now we don't necessarily need the graph, but it is sort of helpful. So we want to know above 65 inches. So up here we already sort of labeled it. So it's going to be to the right of 65. And you notice that that doesn't land on a nice number. So I can't just look at the percentages over here and add them up. So what I'm going to do is I'm going to take, and I guess I should write this down so you've got it in your notes. We're going to put normal dist 69,3, and then we are going to put the min at 65, and then the max is going to be defaulted to infinity. We'll just leave it there. Okay, so let me show you what happens when we do that. When we take the min and we plug in 65 and we leave the max at infinity, it's everything to the right of 65, which is exactly what we want. We want to know what percentage of the data is above 65. So we want to know the area of that shaded region. And it tells us it's 0.9087. In other words, that's 90% of the data is above that. 90% of men are taller than 65 inches. So let's write this out, 90.9%. And we can even sketch that into the curve here real quick. 90.9% of men are taller than 65 inches. Okay. All right, and that puts the video at about 13 minutes. So we're going to do the rest of the examples in a second part. Okay.